Module 3, Queues and Dictionary. So, what we will cover up in this topic happens to be the definition and representation of queue, abstract data type, ADT of a queue, and also a few parts of queue represented using array representation. We will begin with. So, the definition of a queue. Queue, like stack, it is a linear list. It is not a non-linear list. Non-linear list examples are tree, binary search tree. So queue is a linear list. Difference between queue and stack is, in stack, the insertion and deletion happens to be at taking place at one end, whereas in queue the insertion or you call it as push operations will be done at an end called as rear, and the deletion or removal is done at an end called front. So just remember, back, rear is same, front is front, and yeah, front is the first element, front element. So remember this terminologies: front, first element, front part of the queue, back or rear are both same, that is the rear element, the last element. So insertion happens at the rear end, and deletion occurs at the front end. This is how you represent queue. So both ends are used. It is not like a stack wherein you will be using only one end, and you call it as a top. From there you can process. Okay, so this is first example, or simplest example, wherein you have three configuration. First configuration, you have three elements in the queue, and the front element is A and the back element is C. Now if I want to delete an element from this queue, then what we need to do is we need to modify this index position, traverse this index position to the next index and delete this element. Upon doing that, we get figure B. So in figure B, we have only two elements. So front is modified, front is incremented by 1, and the element which was pointed previous to that was deleted off. Now suppose if I want to insert an element, then the back pointer or back index should be incremented by 1. By doing that, we get now B, C, D. Now think as if D is actually the element which has been inserted. So this is a simplest example, the basic sample queues you have. Okay. Abstract data type of queue. So whenever we talk about any data structure, first thing what we need to address is the functions which we are supposed to incorporate onto our data structure. So here the queue which we are going to implement using data structure topology should consist this many methods, and this is the element, and the element over here we require front element, we require back element, and also we require to know the dimension of the queue capacity. For those we will be using private data, and those are addressed in the next slide. So here we just address the instances, the components which we require, functions which work upon this component. So empty, definitely return whether the queue is empty or not, that it should be boolean. Size should determine how many number of elements are exists in the queue. Front will throw the front element present in the queue. Back will throw the back element present at the queue, and the pop function is used for deleting an element from the queue, and push function is used for inserting an element into the queue. So this is your abstract data type. So this doesn't have any C++ programming concept, and it is important. Now this is your abstract class of your queue. So similar to ADT, how you transform this algorithm into a program. So this program is not going to do anything, hence you call it as abstract class queue. It is an abstract class. Abstract class, we don't write any implementation part. So this is just refer the functions which you are going to use, and use a virtual functions saying that it is not going to do anything. So here queue doesn't do anything, and we define empty 0, size 0, front 0, back 0, pop 0, push 0. So this is your template or template abstract class of queue. Template because you can insert integer, floating point, or string, characters, or whatever data type that you require. Fine. Next is the queue representation. First, array representation. We will be implementing queues using array representation. In the array representation, first formula which we can remember as we had used for a stack or even linear list, location of I is equal to I. This is the first formula. So what basically this does is any element you refer this as the element, ith element, zeroth element, what should be its equivalent position in the queue. That is what you're finding. So zeroth element, the position for zeroth element is location of 0. This is used for mapping data from a list to a queue. You are supposed to pass the real-time data from a list to the queue. So the mapping, you can use this formula, but it is not that effective formula. Why it is having a disadvantage. We will see what is the disadvantage. Now for this formula, we use this queue topology now using this equation. So zeroth element, now let's assume that initially the queue is empty. When queue is empty, then we can say, how would you say the queue is empty? For addressing the queue is empty, we will be using this variable queue back. Suppose if queue back is equal to -1, it implies that the queue is empty. Now if you want to insert an element, for example over here 3 elements are added. So right now we will think as if the queue back or the back is -1. Now as you enter an element, you want to add an element item 0. So 0, what happens, the back or queue back will become, increment this, so this becomes 0. So zeroth location, which is actually the queue front, the front and queue front, the front and the back are same, and at the 0th location, queue of 0th location, you put the value which is a. After that, the front is not modified, so you can ensure that for this configuration the front remains same always, but the back is getting modified. So if you want to add a second element b onto this queue, then again we need to change the value of back. Queue back will be incremented by 1. So doing that, the b will be placed at the position 1. So you get this, and finally again one more insertion if you want to do, then again increment the value of queue back and it becomes at the position 2. You insert c. So now again the front is 0. Now what if I want to delete an element? So as addressed, deletion happens through the front end. Now here the problem with this configuration is, if you want to delete an element a, then you can delete it, no problem, but all the remaining elements which are onto the right hand side of this the front element, all should be shifted by 1 unit. So right now we make the shifts, only 2 shifts are required because you have possibly 3 elements. Suppose if there was 1000 elements, then you are supposed to shift, after deleting the first element at the position the front, all the elements from the position starting from the front plus 1, all should be shifted by 1 unit, starting from the length, the total length, till the front plus 1. You have to shift all the elements to 1 unit towards left. So doing that is costly and it is a tedious job. Implementation point of view, it degrades the performance, so we cannot use this configuration. You have one more alternative to solve this circumstance, and that is this, which is location of I is equal to location of front element plus I. So in this case we will modify the front as well as we modify the back, as we had addressed previously the definition of queue. So here this is the configuration where you have 3 elements in the queue, the front, the back. Now if you want to add an element, what basically you do is you just modify the front element, rather than keeping it at this position, you move it to 1 unit towards right. So it does move towards right and destroy the content present at this position. So you get this as the configuration. Now if you want to add an element, then the back will be incremented by 1, so the back position goes here and then you stuff the value. So this will be the configuration. Now the problem with this method again will be, suppose assume that you are having some 8 elements. So what we have here is the front 3 elements you destroy, 8 elements you're having, 3 elements we destroy. So the front would be incremented by 3 and it might point here. Okay, and the back you want to insert, 8 elements were inserted, then you use pop 3 times, so the front will be incremented by 3. Again, one more element I want to add. In that case, you can figure out that we have a space in this array, but the back says that the capacity is full. So this is one of the disadvantage which can be rectified by using this configuration, which means after deleting the front, onto the left hand side of the front, how many number of memory locations you have, those many number of memory location could be shifted to the right of the back. So by doing so, after shift you get configuration something like this, and here you have the memory. So over here you can add an element, but this requires kind of a shifting logic. So for that we use circular queue. So array representation is implemented with the help of circular queue. Then now we will talk about circular queue. Okay, so this is your circular queue representation. What you have here is the parameters, the rear, the front, and this is for the case wherein the front will be always in a position 1 counterclockwise to the front element. So this queue has altogether 8, the capacity of this queue is 8, but the front element is A, so its position is 1 to the clockwise of this the front, or I can say that the front is located at a position 1 counterclockwise towards the front element. This is your front element, and this is 1 unit counterclockwise towards the front element, that is the front. So this is the front pointing and the rear pointing to the last element. Just remember this topology. Literally we expect the front over here, but here this to some extent will simplify the job. That is, if the capacity is equal to the rear element, then this kind of a configuration will help you. We will talk about this scenario when we talk about doubling the array dimensions. Okay, fine. So just remember time being, the front, or it is also represented as q front, is 1 counterclockwise towards the position of the front element. Front element is A. So here basically what we do, if you want to insert an element, so what basically we do is we don't have any index. Index will always be given by this the front, and this may not be always starting from 0. It can change, but this dimension is important. And the location, this is actually the mapping function from where we throw the real world entities onto the queue using circular logic. This is your circular logic modulo operator you are using. So basically what it does, now let's assume that for example we will consider that the front element is at a location. So take this as a location we'll take it as 6. We'll take the front element is located at 6, and this is 7, and this is 8, and the front value will be 5. And how this works, location of I is equal to location of front element plus I. If you want to add one extra element to it, so the rear will be shifted here, this point, and front element which was over here, if you want to delete, this should be pointed here. So you can have a look at the status here. The front, after deleting an element, the element is deleted, then the pointer goes to this position. Okay, we will have a look at this clear cut with an clear cut example what needs to be done. We will figure out what basically here the intention is. Just remember two formulas which is there here. Suppose if the pointer reaches the array length, n minus 1 indicates the array length, then what we have to do is we have to change the rear to 0, shift the rear to 0, okay. And if not, rear is equal to rear plus 1. Directly you can increment the rear. Suppose if it reaches n minus 1, then make rear as 0. So this too can be implemented using one shorthand equivalent representation, that is rear plus 1 modulo n. Same formula is used here. Percentage n minus 1 is that, and this is your index change. Index alteration is based on modulo operator. So similarly, even for deleting we use the same topology, that is if front is equal to n minus 1, which means you don't have any space, front has reached the last position of the capacity which you have, then move back to the first element. From there onwards you might have a space to accommodate your element. If not, increment as usual, incremented by 1. So you can use front is equal to front plus 1 modulo n. So this two equation which is highlighted in bold will be used for inserting as well as for deleting. So remember this equation, and with an example we will have a look at how it is going to help out. So the next one is about the push and pop function. We will just discuss these two functions, and along with this doubling the array, circular array, even that we will try to discuss. With the time being, push and pop instruction we will discuss, then we will wind up. So push function for the queue, this is the program. So push function will take the element and how it is going to insert an element from the position the queue back. Queue back is actually the position from where you will be inserting an element. Let us take an example wherein the element which I want to push onto this queue is F. F is the element which I'll be pushing, and let's have a look at that. This is the configuration which you have, that is QF, that is the front or Q front is pointing to the position 5, which means the front element is located at the position 1 clockwise. So it is at 6th position onwards your Q starts from. Q is starting from 6, 7, then it goes to C, then D, E. That way it continues. So this is the position where the insertion happens through the Q back. So now F is the element. So first you will check this condition. This condition could be avoided now, because this could be used only if you are if you think as if the capacity of the queue is full, then only you are supposed to double the array. Right now we do have capacity, like 3 elements can actually sit on this queue, so we do not have to double the size. So this condition will not be executed. We will talk about this when this condition will be executed and what is the solution for it. So this will be executed only if this condition matches, that is q back plus 1, when this q back reaches qf. Okay, when the value of q back reaches qf implies the queue is full. The queue is full, and also just to discriminate we will be doubling this array length, because what happens initially, queue back and queue front will also be equal when there is no element onto the queue, and also when the elements are filled in the queue. Both cases, queue back and queue front will be equal to same. So just for discrimination purpose, when queue back is becoming exactly equal to queue front, then we have to ensure that at any cost the queue doesn't become full. So to avoid that we will double. So we will be using this code. The code will be explained later. Time being, let us not go through this. We will have a look at it later. So what happens when there is a sufficient memory locations available for pushing a element F? So we have q back is equal to q back. Now the position is 2. So what needs to be done is you use q back plus 1. Q back plus 1 becomes now 2 plus 1. 2 plus 1, so it becomes 3. 3 modulo, what is the capacity of this array length? Array length is 8 now. So 3 modulo 8 returns back 3. So at the position q of 3, at the position q of 3, place the element. So the element is f now. We have assumed it to be f. Place it at the location q of 3. So q of 3 is pointing here at this location addressed by this q back. Place f. So that's how it works. So one push goes like this. Have one more push. Say that you want to place g now. So this, if one more push we have push of g, then again this is not valid. You can go back here. Q back is equal to again 4. It becomes 4 modulo 8. Again it is 4. So q of 4, put g. So you'll get g here. qb will be incremented. The next situation you try, then qp and qf will be equal. So you don't have capacity. Actually you had a capacity, but you will ensure that you will change the dimension by doubling the data. So 2 more iteration if we perform, then the capacity will be filled for this queue. Okay, so this is about push function. So just remember, this is actually the formula which we had talked about. That is changing the index of the pack, or rear. Rear is equal to rear plus 1 modulo n minus 1 or array length. That's what was discussed. The next code is for the function pop. Now how does this work? So similar to pop function, whenever you are using, then the q front element has to be modified rather than uh, q back. So first we check if the q front is equal to q back. So this condition at any cost doesn't occur, because we will be, if that condition to some extent happens here, we will alter the dimension. So you will be having space, no problem at any cost. This condition will not occur. So this condition is true only when you are making the first insertion, that is when the queue is empty. Only at that condition this is true. So that's how we discriminate whether the queue is full or whether the queue is empty. So queue front, when it is exactly equal to queue back, the queue is empty, right? If not, here that is not the case. Let us assume this is actually your data before processing. Before processing, this is the status of the queue. Queue back is pointing to 2 and queue front is pointing to 5. Now we are supposed to delete an element, and a has to be deleted. That's your front element. Front element is located at position number 6, and we need to move this, and we need to modify this q front position. It has to be incremented by 1. So q front, we find q front becomes q front, previous value of q front, previous value of q front is 5 plus 1, it becomes 6 modulo 8. 6 modulo 8 returns 6. So q of q front, what is there at 6th position? Q of q front, that is a, destroy the content, delete the content for the variable t. T could be integer, over here t is a character. So delete for the destructor, use the destructor for t and delete this. So this way you can destroy the element. This is how push and pop function works. Fine. So we will stop for the time being. We will have a look at how do you double the queue when approximately queue back becomes queue front to some extent in the next class.